Hello, this is the next video in a playlist that I'm calling Design of Experiments. It's in my General Linear Models Design of Experiments playlist. Now this is the first part of another little mini-series within that playlist. And this mini-series deals with the regression approach to ANOVA. Now we're specifically going to look at the partial F-test in this video. Now, I'm also going to push you off to a couple videos that I have in my General Linear Models Multiple Regression playlist. And they're titled Type 1 Sums of Squares and Type 2 Sums of Squares. And in there, we talk in great detail and prove a lot of the theorems that we state in this video. Now, as a reminder, the multiple linear regression model is y equals x beta plus error. Now, often it can be partitioned into this group of variables and this group of variables. Now, and then the beta is associated with the x1 and beta 2 is associated with the x2 regressors. Of course, the error carries over. And then if you do this multiplication, it ends up being this way. Now, one of the questions that we ask is, can we drop x2 from the model? And we developed the partial F-test in these videos. Well, the question is, are these regressors helping above and beyond what's already in the model? That's one of the real questions. So to develop some notation for this, and it's the same notation that we used in the background video 1 and background video 2. It's R. So it's R of beta 2 given beta 1. Now this is the reduction in the error sum of squares when the x2 regressors are added to the model containing only the x1 regressors. Okay, so now one little subtlety which will come back on page 2 is notice that we're asking if these set of regressors are helpful. Or can they be added, what's the reduction in their sum of squares when the regressors are added? When we talk about ANOVA models, really the emphasis is on parameters, but in the regression setting, the emphasis is on regressors. Now, recall that the R of beta 2 given beta 1 is this. So this is the error sum of squares when only beta 1 or the x1 regressors are in the model. Now when we add the x2 regressors to the x1 regressors, then we get this model. It's y transpose I minus m y, which when you do that math ends up being this right here, y prime m minus y1 y. Now where m1 is the perpendicular projection matrix under the column space associated with x1, and m is the perpendicular projection matrix under the whole column space of x. Now the degrees of freedom associated with this sum of squares is the rank of the matrix in quadratic form, which is this. And this ends up being a perpendicular projection matrix. So the rank is equal to the trace. And then the trace of m minus the trace of m1 is k plus 1 minus l plus 1, which is equal to k minus l. And l is the number of regressors in the reduced model. K is the number of regressors in the full model. Now the test statistic for this is this. So the null hypothesis is, are the beta 2 parameters 0, meaning the x2 regressors don't help the model predict y above and beyond the x1 regressors, or is one of the beta parameters not 0? And so we prove that this sum of squares in the top is a chi-squared degrees, chi-squared random variable with k minus l degrees of freedom. And of course the mean square error is a chi-squared, central chi-squared, with whatever the degrees of freedom are associated with it. And I have to be vague because, in any design, it's a little bit different. So under the null hypothesis, it's a central F distribution. And then you compare the value that we get with this F distribution, find the cutoff, is it in the rejection region or not? Now, a note that the expected value of the mean squared error is an unbiased estimate for the error variance. The expected value of this partial sum of squares is sigma squared plus this quantity here. Now, under the null hypothesis, so where this this quantity here is 0 if and only if the beta 2 parameters are 0, and that plays a part in the the F distribution. And when under the null, it's a perfect central F distribution. Under the alternative, it's a non-central F distribution. Anyway, so but more detail in that the two background videos. In the ANOVA setting, the model starts out the same. So it's y equals x beta plus error. And then we partition it, for instance, in maybe the one-way fixed effects ANOVA, is it's 1 times x tau. And these are, this is a column space associated with the treatment effect. And here's the beta vector, mu, and then tau 1, tau 2, and however many treatment levels there are, plus error. And you do the math, it can be factored like this. Now, the notation for in the ANOVA setting is very similar. It's R of, for instance, tau given mu. And this is the same. So it's the reduction in the error sum of squares when the taus are added to the model above and when mu is already in the model. So it's interpreted in the regression setting. It's the reduction in the sum squares error when the taus are added to the model with mu in it. Now notice that we focus on the parameters. In the regression setting, we sort of focus on the regressor variables. So here, R of tau given mu. So this is the sum of squares with only mu in the model. And this is actually the total sum of squares if you review some of the previous mini-series in this playlist. And this is the sum of squares error when the taus are in the model. And of course, you take the sum of squares total minus the sum of squared errors, you're going to get the sum of squares treatment. But you do this math and it ends up this. And y prime m minus jy is the sum of squares treatment. Now the degrees of freedom associated with this sum of squares is the rank of this quadratic matrix, which is A minus 1. So the F test statistic for the null hypothesis of that there is no treatment effect versus the alternative hypothesis that there is a treatment effect is this. It's the reduction in the sum of squared error when adding the taus over, when the model already contains mu. Of course, divided by the mean squared error. Now that's the test statistic. Now note that the mean squared error is an unbiased estimate for sigma squared. The expected value of this sum of squares that here is sigma squared plus this quadratic form here. But if in scalar form, it's sigma squared plus n divided by a minus 1 times this sum. And this was covered in much more detail in this playlist of one-way fixed effects ANOVA. Alright, well this is the first video in this series. In the next video, we're going to talk about type 1, type 2, type 3, type 4 sums of squares and how it applies to ANOVA models. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.